So engineers, a lot of times engineers need to extrude fluids through gaps. So let's talk about a couple relevant examples. So imagine I basically have a solid block of material that looks like this, and then another solid block of material that's like this, and pretend that I have some walls on the sides right here. Let's pretend that I sort of wanted to I had some fluid on this side, and I wanted to force that fluid through the gap such that it came out the other side. This happens all the time in bioengineering and in biology, and as bioengineers we a lot of times try to model it. So let's pretend I had a fish. Right? This process is basically happening when the fish exude water out of the sides of their gills. Right? So you can imagine their gills are essentially a little slit like this, and the water that was inside of the fish is now being passed through a gap like this. This happens all the time, so gills. This also happens all the time in injection molding. So, if I have one half of a mold and another half of a mold, and they're coming together like this, and then I inject some plastic into a part of it, that plastic needs to flow and then kind of fill all of the gaps of the mold. And the flow through the gaps is something that's not entirely unlike what's going on here. So injection molding. And if we sort of imagined one half of this, anytime I have some solid surface that's, let's say coming down kind of like this, then a lot of times, the two surfaces coming down sort of squeeze fluid out of the sides of them. So, anytime I have some solid surface and another solid surface and they're coming together and squeezing fluid out of the gaps, that's not entirely unlike trying to force fluid through a gap like this. So, this happens, for example, if you had like two pieces of cartilage of your knee trying to push together, right? So, maybe fluid squishing. So, we care about forcing fluid through gaps of between solids, and a lot of times we need to model the velocities of the fluid and the forces involved, and basically what the relationships are between them. So a lot of times we're looking, for fish through gills, basically how strong does the internal tissues in the fish need to push on that water to push it through. In injection molding, like how strong of a pumping system do I need to pump this fluid, etc. So all the time in bioengineering, we're looking for relationships between forces and pushing fluid through gaps. So this is a perfect example perfect opportunity to do an example problem. And this example problem is going to employ conservation of momentum. So we're going to look at this kind of abstract system here, but you can imagine, it wouldn't be entirely different from some of these other systems right here. So what's this going to look like? So imagine I have this system right here, and over here I, let's say, have some high pressure that's driving fluid into the gap and it's coming out the other side. We're just going to look at the side view, right? So we're just going to look at a side view from this angle right here. So we have a side view of this gap. And let's define a coordinate system. So let's just say I have x as some direction along the gap, and let's say I have z that sort of starts at one plate on the gap and points up towards the other plate right here. Let's say these two plates are separated by a thickness z0 that's known, and let's say I have fluid entering uniform with velocity, let's call it v in. But I know that the fluid exits. With a parabolic velocity profile. Let's say the clouds opened up and Professor Lannin's face came through and said, "Hey, the fluid exits parabolically," and then it closed back up. But that was the only detail that I gave you, right? So let's say we know that the fluid exits parabolically, but we don't know all of the details of this outlet parabolic profile. So let's say there's some V out that's a function of z, right? Because it basically needs to be 0 at z equals 0 and z equals z naught, but it needs to have some maximum somewhere in the middle. And let's say it exits with this parabolic velocity profile that has some unknown constant out front. Let's call it little a. And it's little a times z naught minus z. So let's say, some information about this outlet profile is known, but this constant out front that sort of scales the whole profile is unknown. All right, so we have this uniform V in, this parabolic velocity profile out. Let's assume that if we go back to the 3D view here, this whole system has some width b. So we can basically say the system goes b into the page, right? It's basically some length b in this direction here. So and we're looking for basically if I had this chunk of fluid, let's say I defined a control volume within this chunk, within this gap. Our goal is for this control volume, our goal is to find the sum of forces in the x direction. So we're basically saying, yeah, we know that there's probably shear stress and pressure and who knows what else acting on this system. As of right now, we don't necessarily possess all of the tools to tease out exactly what pressure and exactly what shear stress is acting on this system, but we know they exist, and let's just sort of say, let's look for the overall effect of all of those external forces, right? So we're just basically going to say, we're looking for the sum of x forces, and we're just going to sort of treat this as some single unknown that we're trying to look for in this problem. So as of right now, we basically have two unknowns that we're that are playing into this system. We don't know what this sort of this kind of scaling factor for the output velocity is, nor do we know what the sum of forces are. So what does this mean? This basically says, hey, we have two unknowns. So that means we're probably going to need two equations, at least, in order to solve for them. So take a moment now, pause and ponder. Where are those two equations going to come from? So what will be the source of these two equations that we use to resolve these two unknowns? So hopefully you've had a chance to pause and ponder. These two unknowns, well, if we think about it, we have information about the inlet mass flow rate, inlet velocities and stuff like that, but we don't know information about the outlet. So hopefully we'll be able to relate these two via conservation of mass. So one of our equations is going to be conservation of mass. And then if we're trying to relate forces to things like changes in fluid velocity and all that stuff, hey, if we got to relate forces to something, conservation of momentum is probably going to be our key thing. And if we're looking to relate x forces to changes in x velocities, conservation of x momentum is going to be our best friend. So hopefully these two equations will give us all of the information we need to resolve these two unknowns. So let's proceed. Oftentimes in problems like this, it's usually easier to start with conservation of mass, and then work towards conservation of momentum. So usually conservation of mass, good rule of thumb, conservation of mass is a pretty good place to start. So hopefully you'll use conservation of mass and do this. We've already defined our control volume, right? So what are the steps to problem solving problems like this? We generally organize problem info, which we've essentially already done. We define our control volume, which essentially was already done for us in this problem statement. And now in this case, we're going to want to break up our control volume surface into sensible parts. And then in this case, we're going to apply conservation of mass. And when we do so, we're going to need to deal with the left-hand side. We're going to need to deal with the right-hand side. And when we deal with the right-hand side, we're going to do dot products and integrals. And then we're going to apply conservation of momentum, and we'll deal with the left-hand side, and we'll also deal with the right-hand side, and we'll deal with a couple things when we do with the right-hand side. We'll do dot products, we'll consider what components, and then we'll do integrals. And in some previous problems that we solved, these integrals were pretty straightforward because we had uniform velocity profiles. But spoiler alert, life is not going to be so easy with this non-uniform velocity profile. So we're actually going to have to integrate in these cases. And also when we deal with the right-hand side, we'll incorporate our sum of forces, which is ultimately what we're looking for. So this is going to be our overall problem-solving strategy. Let's go ahead and start implementing it. So let's do conservation of mass. So conservation of mass, left-hand side, ddt of the integral over our volume of rho dv is equal to minus the integral over the surface of rho v dot n dA, and there's no generation term in here. So this is our accumulation, this is our ins minus outs. Oh, one piece of information that I forgot to give in this problem is that we're assuming that the fluid is incompressible. Right, so we're assuming that rho is constant, and we're also assuming that we're in steady state. So we're not dealing with the case where maybe we're fluctuating our flow rate in or flow rate out with time or anything like that. No, we're just pumping fluid in at V in at some time and V in at some time later as well. So how does that help us? Well, if we're in steady state, then basically whatever's going on inside this integral, basically whatever's happening inside our control volume isn't changing with time. So this is basically going to be a constant, and that the time derivative of a constant is 0. So we can basically get rid of this whole first term because we're in steady state. Then we can take this second term and we can break it up into 3 things. So let's consider how we're going to break up our the surface of our control volume. Well, I think three sensible surfaces would be, let's say surface 1 is our inlet. We'll say surface 2 is the outlet, and we'll do surface 3 as everything else. Surface 3 is everything else. So so now the left-hand side is 0, and this is going to be equal to minus the integral over surface 1. Rho is of course a constant. So rho is a constant, and sorry about that. Rho is a constant, and now let's think about v dot n for surface 1. Well, n is our outward pointing normal, so n is going to be pointing to the left on surface 1. Pointing to the right on surface 1 is this uniform v in. So n's pointing this way, v in is pointing this way. They're in opposite directions, so that means their dot product is going to be minus v in. And we still have our dA. Next, we have surface 2 right here. So we have an integral over surface 2. Still have rho. And in this case, v dot n, well, n points to the right. But there's not some single variable v that we can plug in for here. Instead, we need to plug in this whole function for v out. So we're basically going to plug in this function for v out. And it's basically the positive version of this function because n and v out happen to be pointing in the same direction. So we're going to plug this whole function in for v dot n right here. So what's that going to look like? It's going to be a times z times z naught minus z dA. Now, we have the integral over surface 3. Take a moment now, pause and ponder what surface 3 should be. Well, hopefully we had a chance to pause and ponder for surface 3. We still have rho, but if we think about it, n for surface 3 is basically going to be pointing up or down, and there's really not even any velocity right here at the surface, right? Right immediately adjacent to a solid surface right here, we basically shouldn't have any velocity at all. So velocity is 0 right at these surfaces, so that means v dot n has got to be 0 right at those surfaces. So this term basically goes away. All right, so now we have this here. We can pull some stuff out of the integrals. We can at least pull some of these constants out. So I can pull this out and this out. Remember, Vn was uniform over the surface. I can pull rho out and I can pull a out. But of course, these z's I can't pull out because they're varying across this surface right here. So I can at least do some simplifications to this. So now we basically have 0 equals rho b in integral over surface 1 dA. We're going to be able to simplify this in just a second. And now we have minus rho times a times the integral over surface 2 of z naught minus z dA. Okay. So anytime if you have integral dA, then you just get a, and in the case this is surface 1, we basically are just looking for the area of this surface. And if we pull back to this diagram right here, we're essentially looking for the area of this surface right here, of this kind of rectangular slot that we're going in. And of course this dimension is b, and this dimension we basically said was z naught. So in this case, the integral over surface 1 dA is just the area of surface 1, and the area of surface 1 is b times z naught. So where does that leave us? That leaves us with progress that we can make on this first integral. So now we basically have 0 is equal to rho times v in times z naught times b, where z naught times b is the area of surface 1. And now we have, for our second integral, we have rho a and an integral of z times z naught minus z. And in this case, we want to break up this dA. We want to take this surface here and we want to break it up. So take a moment now, pause the video, think about this surface right here. We can kind of imagine the outlet right here. How are we going to break up this? How are we going to break up the outlet surface? What's a sensible way to break up this outlet surface? What should be a sensible dA that we use to break up this outlet surface? So take a moment, pause the video, figure out what we should replace dA with in a sensible way. Well, hopefully we've had a chance to pause and ponder. if we think about it, when we break up surfaces, anytime we have something non-uniform, for example, this non-uniform velocity profile, or in earlier parts of the class when we had non-uniform pressures or non-uniform shear stress distributions, it was sensible to make when we had a dA, to break up that d into one dimension that is a constant and another dimension that our profile of interest is varying. In this case, our profile of interest varies with z. We're going to want to integrate with respect to z. So if we can put dA in terms of dz, that's a sensible thing. And what is dz? dz is essentially a little part of this overall z naught thing right here. And we can basically say, hey, if we carve up our outlet surface into a bunch of narrow rectangles that are all dz tall, but b wide, then our dA is going to be each dA is going to be one of those individual slices. And then when we integrate, i.e. add up all of those little slices, we'll get some output right here. So we have an integral over surface 2 of z times z naught minus z dA, and we're going to break up dA into dz times b, which is the area of one of these little slices. All right, great. So now we can make some progress. We now can go about doing this integral almost. We still have a little bit more work to do before we can do this integral. We need to choose sensible limits of integration. And if we think about what limits of integration we want to choose, we're essentially integrating over this whole outlet surface. So we're integrating from here all the way to here. Well, when we defined z, this bottom point is z equals 0. This top point is z equals z naught. And so those would be the limits of integration when we integrate with respect to z to essentially add up the outputs of all of those little slices. So we're integrating from z equals 0 to z equals our known z naught. So awesome. So take a moment now. Pause and ponder. Can you go ahead and do this integral and carry forth the next step? So take a moment, pause and ponder. Go ahead and do this integral. All right. So integrate. We still have this term here. Rho v in z naught b minus rho a, and I like to distribute this so I have a polynomial that I'm kind of familiar with. Well, when I distribute the z, I have z times z naught. When I integrate that, I get 1/2 z squared z naught, and then when I distribute the z here, I get a minus. When I distribute the z, I have z squared. When I integrate that, I get z cubed, and I'd need a 1/3 out front from having integrated. I still have b. I guess b just sort of carries through the whole business, and I need to apply the limits of integration. So I'm going to go from 0 to z naught. And then when I evaluate it at these limits of integration, what do I get? I get 0 equals rho v in z naught b minus rho a. The lower limit of integration, I just plug in 0 and I basically get nothing. Then the upper limit of integration, I end up with 1/2 z naught cubed minus 1/3 z naught cubed. And this whole bit right here then basically becomes 1/6 z naught cubed. So we can take this integral, and we can take this equation and we can solve it for a, and we end up with a equals the following. We end up with a equals 6v in over z naught squared. Where basically, both the rho goes away because both of them had it. Oh, sorry, I forgot my b. Forgot my b over here. both terms have rho, so we divide it out. Both terms have b, so we divide it out, and we get this algebra. All right, great. So now we have a result here. So we've solved the first part of our problem, which was resolving this unknown constant in our outlet velocity profile that essentially scales the magnitudes of all of these velocities such that mass is conserved between the two of them. All right, so now we essentially have our outlet velocity entirely in terms of known constants. We can basically treat A as a known at this point because we have A entirely in terms of known constants. Woohoo, we did it. So a sensible thing to do is to check to make sure that A has proper units. So if I look at this equation, right here for V out and plug in A, V out has to have units of meters per second, and we hope that it has units of whatever the right-hand side has, right? So A basically has units of meters per second per meter squared, right? V in has meters per second and Z naught has meters squared, and then Z has units of meters, and then Z naught minus Z also has units of meters. So does it work out? Yes. Basically, these cancel out, and we have meters per second on both sides. So that doesn't necessarily guarantee that we did A right, but it at least gives us a little bit more assurance. So check. We're feeling pretty good about A. So now essentially let's treat A. I could carry through this whole complicated term, but I'm just going to treat A as if it's some known constant now, right? Because we have what was an unknown now entirely in terms of knowns. So I'm going to treat A as a known. And that will be a little bit less cumbersome once we now go ahead and apply conservation of x momentum to this result. So we have conservation of, in general, we have conservation of momentum. Conservation of momentum, in general, is d dt equals the integral over the volume of velocity vector times rho dv, and that's equal to an integral over the surface of velocity vector times rho times velocity vector dot n dA plus the sum of any external forces. And we're dealing with the whole vector version now. We anticipated that because we're interested in x forces and because we have information about changes in x velocity, x momentum is going to be our best bet. So now we're going to take the proper component of conservation of momentum. So now we're going to take x momentum. So what's that going to look like? Well, we're going to take the x component here, but we're also going to apply our steady state assumption. And if we apply steady state, we can basically get rid of this term. So sorry, I jumped the gun. So first, let's apply our steady state assumption, get rid of this term, and then let's take the x component of this. So that means we have 0 is equal to minus some integral over our surface of Vx times rho times V dot n dA. Remember, when we're taking a component of the conservation of momentum equation, we take components of the lonely velocity vectors, but we leave our V dot n's alone. And when we're taking a component of this, we're basically looking for the x component of our external forces. So what do we have here? We basically have, this is this term, this is that term that we're looking for, the sum of external forces on our control volume. So we're basically just going to treat this as some unknown constant that we're ultimately solving for. So basically, what's the deal? As long as we can square away this integral over the surface, and of course we're going to break it up into the 3 parts that we did before. As soon as we could square this away in terms of known constants, we're in business. So let's break up this integral into the 3 parts for our 3 surfaces and proceed with trying to solve it. So an integral over surface 1, Well, what's Vx for surface 1? Vx for surface 1 would be positive V in, because V in is going in the x direction, so it's a positive velocity. Then we have rho, and then we have V dot n for surface 1. So V dot n for surface 1 is going to be minus V in. And then we have our dA right here. Then we have minus an integral over surface 2. If we think about surface 2, that's the outlet right here. So Vx on surface 2 is V out. And then we have rho. I'll sub this in just a sec. And then V dot n for surface 2 is also V out. So we get two V outs. They're both positive. One because V out is in the positive x direction for our Vx. In this equation. And then another positive V out because V and n are in the same direction for the outlet right here. And then we get dA. And then we have minus an integral over surface 3. Well, basically surface 3, Vx is 0 and V dot n is 0. We have a rho, I guess, but who cares? dA. And then we have our as of yet unknown sum of forces in the x external forces that we're carrying through with our conservation of momentum. Okay, we're getting close. So we now want to take our V out, which now is in terms of a known constant A and this other stuff, and we need to sub it in essentially twice, once into here and once into here. So we're going to essentially take this and square it and plug it into that integral. So let's do that. Meanwhile, we can also pull out these constants from this integral here. So we're left with 0, rho Vn squared, integral over surface 1 dA, minus rho integral over surface 2 of a squared z squared quantity z naught minus z squared. And we can make the same substitution for dA that we did earlier because we're integrating in the same slicey sort of way. So in this case, it's just going to be b dz. This, of course, that one was 0, and now we have our plus the sum of all x external forces. All right, so take a moment now, pause and ponder. Can you go ahead and do this integral? There are a couple ways to do it. My favorite way is with Wolfram alpha. But, feel free to use whatever you want. I mean, the tricky thing with Wolfram alpha is, like, you plug in some result, you better be sure you plugged it in right. Because you get some result, you just cross your fingers and hope you did it right. Wolfram alpha is a bit of a black box. Calculus is not a black box. So I'm going to proceed with showing the steps, but, you can either try to do it out by hand, use Wolfram alpha, but, it's good practice to try to do it yourself. So pause the video and try to do out this integral yourself. All right, so hopefully if you paused and pondered, let's now proceed. We can square away a little bit more on this first term before doing too much on this integral here. So that's basically going to be 0 equals rho Vn squared, and then integral of dA over 1 is just area of 1, which we already figured out was b times z naught. Now we have minus, we can take out a b and an a squared, so we have rho a squared b, and then we have an integral of z squared, and we can FOIL this first bit, so we'd get z naught squared minus 2z z naught plus z squared dz, and we still have our sum of external forces. We can, of course, take this z squared and distribute it over all the terms here, and our limits of integration should be from 0 to z naught in the same, because we're integrating over essentially the same surface that we did when we did conservation of mass. So we now have 0 rho vn squared b z naught minus rho a squared b, and when you integrate this, you get 1/3 z cubed z naught squared. You get, when you distribute this, we get you get z cubed, so now we have z to the 4th, and when we bring down the 1/4 and combine it with the 2 here, we'd have a 1/2, and then we'd have and then sorry, I forgot the z naught that's in the second term right here. And then in the third term, we'd have a z to the 4th, which when you integrate it, we get z to the 5th, and we'd have a 1/5 out front. And this would be evaluated at the limits of integration from 0 to z naught. And then we still have our sum of external forces, our x external forces. All right, so when you plug in z naught for all this, some stuff simplifies substantially, and you end up with 0 equals I guess we can factor out a rho from both terms. And what are we left with? We're left with rho. I guess we're left with rho vn squared b z naught minus rho a squared b, and we'd have basically a z naught to the 5th. And the coefficient that you get when you cancel off all of this stuff out is, you end up with 1/30th as your coefficient here, plus our sum of x external forces. And then if you go back to the result that we got earlier for whatever a was, 6vn over z naught squared, and you plug that in for a squared right here, you end up with, and then solve the whole overall equation for sum of x external forces, then you end up with the following result. You end up with rho times, let's say, minus b v in squared z naught plus b v in squared times 6/5 z naught. So if in a sense you look at this first term, we have, this is the momentum entering, and this is the momentum exiting, or I guess strictly speaking, it's just these terms here. That's the momentum entering if you distribute rho. So interestingly enough, these two terms look pretty similar to one another. They basically have a b vn squared z naught, but the exiting term has this 6/5. So interestingly enough, if you took a uniform velocity profile and then distorted it to make it parabolic, even though the mass flow rates in and out are the same, the outflow actually has a little bit more momentum then the inflow, which is an interesting phenomenon. And it basically has to do with when before we integrated, we squared before we integrated, and that caused this sort of non-linearity that caused a mismatch in momenta between the two. So interestingly enough, we actually get more momentum exiting. It's basically like the square of the sum is not the same as the sum of the squares, so we end up with more momentum exiting than entering. So even though we have the same mass flow rate in and out, we have more momentum out than going in due to the distortion of the velocity profile. And that is basically saying, hey, you're going to need some force, some externally applied force from pressure and from shear stress and from everything else in order to accomplish that change in momentum of the fluid. So hopefully this was a useful example problem following the structure that we have here, where we can combine both mass and momentum conservation to solve for a couple of unknowns in a system that is potentially relevant to bioengineering. So thank you for listening. Good luck with your fluid mechanics studies.